Hi, hello students. So welcome to my course on foundations of generative models, or we have titled this Introduction to Generative AI. So we're going to talk about the state of the art models in this course. So what we're going to do here is we'll be talking about the latest models in the field around us. So AI is really catching up, and we can see uh, how chatbots interact like intelligent agents currently. So latest models around include Dolly, ChatGPT, and so on, VO. So they do a lot of tasks, including image generation, chatbots, and video generation or audio video visual generation. So the entire idea is that the entire world around us is revolving around what is called generative AI, that is able to create new or novel sort of information. So, uh, till very recently, AI was used for classification tasks, for example. It was often used for discrimination. It could be used for regression, for predicting your people who have done all the previous courses. I'll be attaching the link to previous courses, which talks about introduction to machine learning and reinforcement learning and linear algebra and probability, which are sort of prerequisites, except the RL part, all are prerequisites to understand what is generative AI, because we'll be dealing with probability and linear algebra a lot here. So yeah. The entire goal that we have is to understand these models, which are not just going to give you predictions. Instead, they would be giving you data itself. For example, it could generate a human face, where it will not give you a prediction. You can make it predict things like if it is a male or a female, but it's a more difficult task to tell the model, please give me a female face, and it generates a female face. So let's get to some of the recent models that we have before we get into the details of the course or detail of the material of the course. I'll be talking about what is the form, or what form are we going to have the course. So this course would have around 12 to 14 sessions, depending on how much we can cover. And we are going to cover a wide range of details here, including variational inference. Then we'll follow. They include a lot of models. This will be taking up most of our times, including mixture models, PAEs, diffusion models, and so on. So these type of models we would be covering. We would be doing adversarial training like GANs. We'll be doing autoregressive models. And if then time permits, we'd also do recognition based models, probabilistic models. So each of these sessions would be around 1.5 hours. Typically, when you are studying, it will take you around 2.5 hours to complete each of them. Um, the material is worth 2.5 2 hours of information. So currently, what I've planned to do is, since a lot of people have exams and things like that during this period, and I'm a bit busy uh, with my research, I would record these sessions and I would upload them onto IEEE website and with YouTube, and people can follow them. There'll be like three sessions per week, hopefully, and we'll be able to complete it between 3 to 4 weeks. And then we'll be having, so we will have recorded videos. So all of these would be recorded videos. This would help people do the lectures at their own ease rather than having a fixed time, which has been difficult in the past few years in my experience. So, but there is a deficit when we have pre-recorded videos that we want students to interact. So every 4 sessions or per assignment, that's roughly how I'll be structuring it. So I'll have 2 assignments, say around the 6th session, after the 6th session and the 12th session maybe. So this is the rough idea that I have. And after these two, I'll be having a doubt clearing session that will be live. This will be live, and people, after solving them, can interact with me. And other than that, I'm always available on Teams. You can, I'll be giving you homeworks. You can post them and I will tell if the solutions are correct and so on. So before I go into the material, so that will be the overall goals, and we'll have coding assignments and mathematical questions that you have to solve as a part of your grading if you want me to check your assignments and things like that. So what I would be doing in this course is, so hello, I'm Moinak. I'm a 5th-year PhD student at the Indian Institute of Science. So I have been teaching courses as a part of my PMRF teaching requirement, and I've taught probability statistics, linear algebra, optimization, machine learning, reinforcement learning, and most of these courses are actually prerequisites to our course. So I'll be attaching the links to all of the courses in the description, and then you would be able to go into and see if there are some concepts which I'll be referring to. So most of the topics will be self-contained, but it's always helpful to have the linear algebra, probability, and machine learning views of things, which we have already covered in the past few years. And you can always go back to those sessions. They're all structured very well, and you can just see the relevant information if something I refer to has been done in a previous course. So yeah, because this is a very advanced course, fairly advanced course, and people having some background in statistics and linear algebra and machine learning is very important in this. So yeah. So now let's get started. I have given a broad introduction of this course, and I'll not be talking logistics anymore throughout the course. We'll be delving deep into the material, which would be deriving models. So a lot of people who have done machine learning and deep learning that I have taught or in other places we have concentrated a lot on architecture of models. So this course would be less of architectures because we would be assuming neural networks to be function approximators, that there could be a linear layer, they could have a long, deep neural network and things like that. At the end of the day, they are all function approximators is what you'll be seeing. So I'll not be drawing out architectures and showing how CNNs work and RNN works, and because this has already been covered in introductory courses in classification models and things like that. But sometimes maybe when I'm doing autoregressive models, I'll be dealing a little with transformers, because that is the state of the art in the field, and people may not cover them in the introductory courses. Other than that, we'll not be talking about architectures because architectures are trivial. Once you know that the CNN has convolutions and feed-forward networks are just products of matrices, you can just plug in any network, and at the end of the day, what is important is how you train these networks. So any network you train, based on how you train and what you make them do, these models can do wonders. So for example, if you train a model to just do classification, it will never generate human faces. But the same model, if I go and tell them now, this is my objective that we'll talk about what objectives are, generate human faces instead of just classifying, that same architecture maybe adapted just based on training the model to do generation. So there it goes. So this is the high level motivation, you can say, just in words, so of what generative AI is. But now let's see some specific cases. Why should you have the hype of these models? I think all of you have used video generation models and image generation models. So for example, Dolly, when it came out, it was a huge thing. And this is the first diffusion model paper on, this was called the DDPM paper, the probabilistic diffusion denoising model. We'll discuss this model. So this is denoising diffusion probabilistic model. Denoising diffusion probabilistic model. So this is diffusion model, and we'll talk about them. But the takeaway is these models can generate human faces at the accuracy or at the quality of where you cannot really identify which of these following are real human faces. So for example, if I have these 4 faces, I found it for the first time very, very difficult to identify which was a real human face and which was generated. So this is a giveaway that this was the real face. And the rest of them are all generated. And surprising that I just conditioning on saying that give me a female face, it just gives you a perfectly plausible real face, which may not actually exist in the world. We'll see why that's what I'm saying, because these are all perfect models which will never be able to replicate data that has learned. It can generate data close to it, but how the model has been defining the exact same face that it has been trained on is a zero probability set, because things like diffusion models do things on random noise and they denoise them and things like that. So they trained well, they would not generally create data from the training set, and they would be always creating novel images. So, okay. So this is one of them. So where you could create human faces. So wonderful. The other thing is now after this, so we went to what is called stable diffusion. In stable diffusion, what we saw is that you can condition not only based on a single category, say here female or a female face, you can do it using entire strings of sentences. So for example, a crowded metro station or a cat in a laboratory, it just creates, they're all generated images from Dolly. It's unbelievable that it can just give a prompt to the model. Now this has been integrated with all the chatbots, and you just give it a prompt and it will run a diffusion model at the back and give you an image. So yeah, so generating images from text is also a very, very big thing. And once it caught up, the stable diffusion caught up, it was a big thing. So one of the papers that did such well on diffusion models was called Latent diffusion model. And this was a very, very influential paper, which was rather adapted into doing this stable diffusion and things like that. So other than that, people have used these generative models to reconstruct data. For example, now I conditioned this on text, right? So now it's almost a sci-fi movie. So once this Takagi et al. Paper, this is by Takagi et al. Very recent, a couple of years back, 1.5 years back, this paper came up, and people were astounded by what the results that it was giving. So here we had human participants see images, and their fMRI activity was recorded. So what is fMRI? fMRI is functional magnetic resonance imaging. So you all know what is MRI. It's the scan of the brain. And this gives us a functional scan of the brain. It tells you where blood is flowing in the brain and how. So it tells you which brain region is active. So this gives a proxy to the activity of the brain, where telling you where the blood is flowing and things like that, and how the brain region is active. And this patterns would give you which of the images activate which regions and what are these fMRI signals. So given this fMRI activity, say this is an fMRI activity, we have flattened the fMRI activity, which is a 4D scan, because your brain is X, Y, Z and scanned over time. So we flatten it, pass it through a model, generative model. Here too, it was a diffusion model, and then it was able to recreate what you saw. So here, be it fMRI, be it text, it is able to give you the information about which image is most likely to go with this pairing. For example, the text and with the image and so on. So people have done it with texts and so on. So other things people have generated graphs. So this is a lot of graph generation so you have done what is called in chemistry for drug discovery. We have AlphaFold, which predicts if a particular protein will fold or not. There's so many such algorithms. This is text model, ChatGPT, which would tell you the next word or phrase and would generate entire sentences based on your prompt. So this is the ability of this model. So given the prompt, this model can generate entire sentences. And this is where these are called autoregressive models. What it does is, given a set of words, word 1, word 2, word 3, it is going to predict the probability of word 4, given predict word 1, word 2, word 3. So this is actually going to give you a list of sentences. It'll break this up into probabilities. It will create this word 4, and then it will create word 5, and so on. This is how a ChatGPT actually works. So we'll see all of these in details, but yeah, it can create sounds. You can see VO, it just creates video plus sounds. It's phenomenal what these models can. And they all sound like humans talking. So yeah. So as I told, the prerequisites of probability, we'll be doing a lot of probability here because all these models at the end of the day are probabilistic models. We'll be talking about linear algebra. Basics of machine learning is also required, where you do some optimization and things like that. And you can please refer to the contents of Introduction to ML, and it covers most of these topics in details. So, okay. So now enough of the hype around those generative models of images, texts, and videos and audio and whatnot. Given fMRI, it is able to tell you what you actually saw. So if you took away something from this presentation, is all these mock papers, is this phenomenal idea that even very, very complex data, for example, brain data, can be used effectively by these models to actually read your mind. So you're actually telling what you actually saw. For example, if you saw this watchtower here, sorry, I didn't mention it. These are the real images you saw. The model created these images. So this is what the model created. Given the fMRI. This is the original. You give fMRI. Remember that you only gave fMRI. Model created on giving fMRI only. So that's what is very, very surprising, because you can see the entire concept of a train and a watchtower and a watchtower is actually captured by the model. It knows that this brain activity corresponds to when you see a watchtower. So yeah, this is a very, very powerful model. I think I can have got you very excited to learn more about them. So these are very advanced stuff. So to get into those, we will have to build one stone at a time, and we'll be starting off from the basics, revising what were discriminative models and what are generative models. So if you remember from our previous courses, a discriminative model predicts the probability of a label given the data. This is a label, and this is input features. Right? So you give this model some input features and it will make a prediction. So for example, say you have this red and blue dot. If I give you a dot over here, it will say this is more likely to be in red cluster or red class. So we know that. So there is this data in discriminative model is often in the form of labeled data, which is you have n data points. Say you have n data points. These are features. It could be images, text, or any EEG or fMRI, whatever you want. It could be any form of data, and Y is what you want to predict. Right? So this model has a fundamental drawback, and it has a missing link in it. What is the missing link? You can never ask the model if you can generate data. You can generate new samples, or you can never ask the model to generate new samples. So okay, so the model will not be able to give you new data points, and that's what makes this models have a little bit of a drawback in themselves. On the other hand, if you see this type of a model, this is called a generative model, where instead of just drawing this decision boundary, which the discriminative model does, it's called a decision boundary. So if you are on one side of the decision boundary, you say you are in the one class, and the other side of the decision boundary, you say it in the other class. You could also do regression and things like that. But in regression, it will just be a fit to the line and things like that, fit to the data that you have. This is regression. But given a new data point, you can just make a prediction of its output. That's all discriminative models can do. On the other hand, generative models, given the same form of data, models this joint distribution of the labels. If the labels are available, if they are not available, you can even model just the data's distribution if labels are not available. You can also do conditional generation. That is, what does it mean? So here you're trying to, for example, you look at this plot over here. You are trying to generate a model which predicts the probability of a feature. Probability of feature given label. So now this entire problem has been shifted. So instead of modeling x given y given x, where you're making a decision, I'm going to model this. What is the probability that given the data point is class 1, that these are the features corresponding to the data point? For example, these points over here, I'll just draw them. So for example, these points over here, if you tell them that they're in class 1 and you give these features to the model will say they have high probability. And once you're able to you know this distribution, learn this distribution, so you can always sample data from sample new points from p theta of x given y. So now if you know your so let us talk about what unconditional models are and what conditional models are. So either data could be labeled or not labeled, as I was telling. So if your data is labeled, so you have x and y pairs. If it is unlabeled, it's just features. And remember, each of these features could be in some d-dimensional space. And this could be an image. It could be 256, r to the power 256, 256, 3. Or it could just be r to the power 100, where there are 100 features, or things like that. X could be anything. It's a multi-dimensional data, and whereas Y is a label describing the data. Y again could be R, it could be some category, could belongs in some category, C1, C2, CK, and so on. It could have K categories as well. It could have RK, for example, if you have a text input, text prompt, and so on. Text prompt, right? So it could have classes, it's just labels describing the data. So what is the underlying distribution you sample from? You say that this data has been sampled from an underlying distribution Px. On the other hand, this data has been sampled from this joint distribution P of x comma y. Your idea is to model for unconditional models just P of x. You will learn a proxy for the underlying distribution. Here, your idea is to learn P theta of x given y, P theta of x comma y, either of these, and you'll be good. You'll be good. So now, what can unconditional generation help you do? So once you have, as I was saying, once you have sampled, you learn the distribution. For example, you have learned data belongs in normal 0, 1. So you can just say that new data point xi, you can just sample from normal 0, 1. Another example is, you can say you have learned that data comes from a coin toss. Coin toss. That is a Bernoulli P random variable, right? So you could say that just give me a new data point and I will toss the coin, right? I'll give you, that is a sample from the distribution. So you could sample, once you have done that, you can tell what is the likelihood of the data. This is called likelihood, the log likelihood of the data, where you say under the model, what is the probability of the current data? And you can find out outliers. If the likelihood of the data is small likelihood, you can tell them they are outliers. Similarly, for conditional models, you can do conditional generation, say generate a female face, where you will condition y to be a female and you'll get a generation of a female face. You could have conditional likelihood similarly, and you could make classification. So if you know your probability, so P of y given x is just, if you learn P of x given y, it's just multiplying P of y, which is just the marginal distribution. And you will have a P theta of x, which is generally constant, because you're summing over all classes. So you treat them as constant. You just say it is proportional to P theta of x given y and to P theta of y. So if you have this priors on y, just multiply. For example, say you get a face, for example, you want to make a prediction whether this face belongs to a man or a woman. So you will just say, for example, P of y equal to woman given face I is equal to what you know from the model, what is the probability of the face I given the label was a woman into P theta of woman. Say you get in the data 50% of the times it's a woman. So you can so it is just this probability which will be using to make a prediction. So if this is more than a man's, so you will compute this. Similarly, you will compute P of y equal to man phase I, and you'll get P theta of phase I given y equal to man and probability of a man. So you'll see which of them are greater and you'll make a prediction accordingly. So the maximum will be used for making a prediction. So that's it. So you can see that once you learn a generative model, you have multiple advantages. Not only can you make classification like discrimination models, you can also detect outliers. You can assign log likelihoods, and you can do a lot of things. You can generate data and the never-ending advantages. So, okay. So people who have been wondering what is likelihood. So let us define what is likelihood. Likelihood is how probable is the observed data given the model. So it's basically how good is your model fit? How good is your model fit? How well the model explains the data. Right? So we have done this in the previous courses. We have done maximum likelihood estimation and things like that. So if you have to write it in Bayesian format, you write it P of X given theta. So where theta is the model. But since we will parameterize models using neural networks, I don't want to write conditional probabilities for the models here. So instead, what I'll do is I will parameterize. So what I'll do is I'll parameterize the probabilities with theta with the model. We have done this in the past where we have predicted what we have done in the past is where we have predicted what is the probability P theta of y given x in terms of maximum likelihood estimation and things like that. So we'll be writing it this way. How well is the probability of the data given the model? And the log likelihood is generally what we'll be using. Log likelihood to learn the data. Learn the model fit. So it may be looking a bit abstract currently. So let us try to understand what this actually means. So let's start off with this first question, or this first idea of minimizing divergence is to train generative models. And what is minimizing divergence is what we'll be seeing. I'll come back to these. So first is we'll be talking about the pullback Leibler divergence. Or the KL divergence. And I will tell you again. So first, remember data. This is your data. Data xi currently, I'll be only assuming that xi has both data and features. So if you have both data and labels, what you can do is you can put the labels as one more dimension to the data. That's all you can do. So say, for example, if you have a 10-dimensional data or 10 features, what you can do is you can add y here and say this is my new data. So you can always do that. It's not a problem. So I will say that let data, say you have data, n samples from the data, and you have sampled it from a underlying distribution px. This is the underlying distribution. So what we want we want Px. Once I get Px, I know everything. But the problem is I don't have, the issue is no access to the true distribution. So we have to approximate. We have to approximate it from the data. Okay, so one of the ways we had done it in the past is by doing maximum likelihood estimation. If you recall, what was maximum likelihood estimation? Say if I have all these model parameters, so these are model parameters theta, and this was my likelihood, log p theta of x, I would choose the best theta that explains the model, that has the maximum likelihood, maximum probability of being observed under the model. So Emily would tell me theta star was the maximum value, or the parameters correspond to the maximum value for the likelihood or the log likelihood of the data. And here for the entire data, and our assumption is that data is IID. Data is IID, independent and identically distributed. Distributed from Px. So what we can do is, we can say that P theta of x can be written as a product of I going from 1 to n, the in data points of P theta of xi. And therefore, we can say that the corresponding problem is equivalent to, right, minimize or maximizing the sum of likelihoods or log likelihoods of the individual points. So this is what we can say, right? Now, these are also equivalent to saying, if I write this as equivalent form as arg max of theta, if I multiply with n, and I just multiply with n in and out, inside and outside. So this is the same expression, right? But guess one thing, that if I have a constant that is multiplied to an expression, so for example, 1 by 5 into x squared, the minimum of 1 by 5 into x squared is the same as minimum of just x squared. So multiply a constant to a function that varies doesn't really change the point where you get the maximum. Sorry, the minimum, the arg min is same, sorry. The minimum may change because you are multiplying it to the function, but the argument that minimizes the function will be the same because it's going to be the same point. So any constant, if you multiply or add, the argument that maximizes or minimizes should be the same. For example, if I have x squared to be the function, and I have another function to be x squared plus 2, you see both of them are minimized at 0, right? So I can say this is equivalent to saying 1 by n I equal to 1 to n log p theta of xi. So now people who have done a little bit of probability or similar to my course can say this is what is this? This is equivalent, or this is a sample mean, sample average of log p theta of x, which means it is a Monte Carlo estimate of the actual expectation. We don't have the data, therefore this is equivalent to, if you do not have the data, to writing this is equal to arg max given theta of the theta, and this is the expected value of x sampled from the underlying distribution. So remember, xi's are sampled from px. That's the reason I'm going to write log p theta of x. So the I can just be removed because it's a variable. And you can see that it turns out to be an expectation. So when it's an expectation, this is equivalent to saying this is equal to, if you had the distribution, it is equivalent to saying argmax over theta integral of px log p theta of x dx over all x. It could be a multi-dimensional integral, but if you, this is basic probability, we know that when expectations are computed, if you have by law of large numbers, the 1 by n f of xi I equal to 1 to n converges to the actual expectation of x in the same px of n tends to infinity. This is called law of large numbers. So if you have the same function, if you take the sample mean of the function, you'll get the same value. So therefore, this helps us solve this very important problem. Although we don't have access to the underlying distribution, the data gives us the likelihood itself, because we can do what is called as a Monte Carlo estimation of the expectation. So now I'll tell you, this is what we had done in maximum likelihood estimate. And we had done in the previous courses multiple estimates where we were able to estimate the parameter of a Bernoulli random variable, or be it an exponential random variable, and so on. What I'll today do is I'll show that doing this maximum likelihood estimation is actually minimizing a metric that is called the KL divergence, that I just called as Kullback-Leibler divergence between two distributions. Now say I'll draw the two distributions. This is P of X. This is the actual data. So in our course, we'll be primarily dealing with PDFs. We will assume density function exists, right? And once the density function exists, we'll be able to do all these things much simpler, because your all these things are just defined in terms of integrals of the densities. So say this is your P of X, and this is P theta of X. And this is your X, and this is the along which you have the density. And you can say this KL divergence defines the distance between these two distributions. That is, it's a matrix. So if so, what are the properties we want? P theta of X equal to Px, then this KL divergence. So we'll write this as between two distributions, say KL, or we'll write this as DKL of P and Q. So if P theta between P and Q, right? So if both are equal, we will say that the KL divergence between Px and P theta of X is equal to 0. And we'll have to define a matrix for which it is true. So let us define how KL divergence is defined. So this is defined as the integral of Px log of Px by Qx dx, right? Assuming there is support for the entire X, you can always add epsilon to have support, so that it is no division by 0. No division by 0. So this is for a continuous distribution. For a discrete distribution, this is just P of X is equal to some category, log of P of X equal to that category by Q of X equal to category over all the categories in the classes. So this is the same thing. This is the discrete analog. So let us see. I will show you that minimizing. So MLE, I will show you, is equivalent to minimizing this distance. So theta star R min theta of the expected value of X log P theta of X, this is MLE, is equivalent to minimizing. This is argmax. So maximizing likelihood is equivalent to minimizing the KL divergence of the data and model. So we can write this as dkl px p theta of x. Now let us see why it is equivalent. So we are trying to find out the KL divergence between the data and the model that we have, and we'll show that it is equivalent to having the expectations of over the data itself for the likelihood. So I will write this as px log px by p theta of x, and this is minimum arg min theta dx, right? So now if I write this as the integral of log px log px dx minus px log p theta of x dx, you can see this first term is the entropy or the negative of the entropy of this probability function. But this is independent of theta and is constant. Since it is constant, this is equal to writing minus the x. See, this is again an expected value of x sampled from px log, I can put the x negative inside, dx. And this is arg min over theta. So negative, if you have a negative sign, if I consume the negative, this is equivalent to writing arg max of theta, the expected value of x in px, log of p theta of x, right? So these are equivalent things to write. So what did we just learn? We learned that the minimizing of log likelihood, or minimizing of KL divergence between two distributions, that is in px and p theta of x, is equivalent to maximum likelihood estimation. So I will talk about two properties of the KL divergence. One we already saw is if P and Q are equal, dKL P and Q is equal to 0 if P equal to Q, if and only if P equal to Q. Second property is dKL PQ is always greater than 0 if P not equal to Q. We'll see these two, right? And the other property, I think we saw the distance. It's distance, so this is a matrix, so that it says that. And the third property, it is not symmetric. That is dKL of PQ is not equal to dKL of QP. Okay. So the first property is very simple. You can just put it in the equation, Px log Px by Qx dx. And if I equate it to Px, because they're equal, I can just set it to this log of 1. This is Px log of 1 dx, and this is just 0. Similarly, I can also have this third term to be very simply done. So Px log Px by Qx dx clearly is not equal, may not be equal to Qx. There's no guarantee they will be equal to Qx by Px, right? So one is an expectation over Q, one is an expectation over P. The distributions themselves could be different, and therefore there's no guarantee that they could be same. They would be same. So this is not symmetric. The third and the most interesting property is showing that the KL divergence is always positive. That is dKL P and Q is greater than 0 or greater than equal to 0, where equality only holds for P equal to Q. So let's look at this once. So how do we do this? So let's write this down as Px log Px by Qx, right? This is the KL divergence. which is also equivalent to writing the expected value by Lotus. We have learned this in the past. So this is, you're taking an expected value over this density. So this is the function that you are taking an expected value of. So we know that the expected value over a function P over a PDF or a PMF P for any function X is the integral of Px fx dx. We have learned this in Lotus in probability and statistics, that you take the function, pass it through the function, and just multiply the corresponding Px and take the integral over all the data. So that's the expected value. So X in Px, so it's just sample from Px. So this is just going to be this is the function. So you have to be very quick in writing these expectations, right? So whatever is in the whatever is multiplied with the function is going to be with the PMF or the PDF in this case, or the distribution density function here is going to be the function that you're taking an expectation over, right? So you're taking expectation over log P by Q. So now this, if you recall, you can write this as minus log Px or Qx by Px. I'm just inverting the signs. So now, if you recall Jensen's inequality, so minus log is a convex function. I'll show you why it's a convex function in a while. I'll just complete this proof and we'll come to that. Minus log is a convex function, and we know for convex functions, the expected value of fx is always greater than f of expected value of x. Right? So it's like taking the log or the negative log outside and taking the expectation inside. So the function here is f is equal to log here, and log has some parameters inside or some arguments. The argument is q by p. So the function is negative log, sorry, and I'll just put, this is what I'll write this as, right? So as soon as I do this, you can clearly see this is minus log integral of px qx by px dx. So this two gets cancelled. So you have, this is equal to minus log integral of qx dx. So now what is the integral of a PDF over the entire data? This is just equal to 1. That's how a PDF is defined. So this is equal to 0. So log of 1 is 0. So we can say that DKL of PQ is greater than equal to 0. So this is what we can prove. Assuming the convex function. So why is it a convex function? What does a convex function mean? We've already done it in the past. I'll give you an intuition. A convex function has the following property. So it is upward facing function. Upward facing function with the following property, that f of alpha x plus 1 minus alpha y is less than equal to alpha times f of x plus 1 minus alpha times f of y. What does it mean? It means that you take any 2 points x and y on this axis, you connect them. This is nothing but the midpoint theorem, right? This is connecting these 2 points, all points connecting these 2 points. You can clearly see that all these points that are being connected, they're below and if you take the function values are always below. This is your f of x and this is your f of y. So if you connect these 2 points, all these points are above. If you take a point like this, alpha times f of x, or if you take a point in between, which is alpha times x plus 1 minus alpha times y, the function value at this point, that is below this value, right? This is a convex function. Or the second property is the second derivative of this function is greater than 0. You can clearly see it's an upward facing function. If it's an upward facing function, second derivative is always 0. We know it from elementary calculus. right? So again, if you want to visualize this, I'll write it down again. So this is the function between any x1 and x2, or x and y, two values. Anything in between, that is alpha x plus 1 minus alpha y, where alpha is between 0 and 1. You can see once I take a function of that, f of alpha x plus 1 minus alpha y, this is going to be below this value. This is f of x, and this is f of y. So this is the value where it is alpha times f of x plus 1 minus alpha times f of y, right? So this value is, or this line always lies above the curve. So it will never be equal, never be less than the function value at that point, right? So now let us look for log value. Is log minus log x a convex function? We'll be using it extensively. Is it convex? Question. Let us look at it. So we know that the log of x is something like this. This is your log x. This is x log x. So your negative of log x is, or minus log x is just going to be this, isn't it? Correct? So as x increases, it will go towards minus infinity. As x goes towards 0, it will go to plus positive infinity. So you can already see this function is actually facing upwards, right? So when you take a negative of a function, you flip it over the x-axis, right? That's what you do. Flip it over the x-axis, because for all values which the function was positive, it becomes negative. Now, once I do this, I can also show it the second derivative of log x, minus log x, is the first derivative of minus 1 by x, which is equal to 1 by x squared, which is greater than 0. Right? For all x greater than 0. So it is clearly a convex function. So if it is a convex function, this will hold. The Jensen's inequality will hold. This is called Jensen's inequality, which you have used. This is going to hold. Now, why will it hold is a question to ask. So if there's a very, very simple reason to, very, very simple way to remember this, right? How will we remember this? So the Jensen's inequality again, if I write it down again, if f is convex, remember that if f is convex, this is a property, if f is convex, minus f is concave. And both these functions are same. You can just invert the signs wherever it is below this, you see this line between 2 points, line connecting them is below the graph. So this is whatever happens for a greater than sign will become a less than sign here, and so on. So if f is convex, in Jensen's inequality, what do we know? We know that the expected value or of fx x under some distribution is going to be greater than f of expected value of x. Right? That's what we did. We pulled out the log here, and we said that the log, as soon as I pull it out, or the negative log, the expectation can be inside the function and it will be lesser. And now how do I remember this? We have proved it in the past in math for ML, but I'll show you an intuition of how to do it. Say this is your convex function. This is your f of x. And this is x, right? So now take 2 points, x1 and x2. It's very similar to the convexity principle I showed just now, x1 and x2, right? So now between these 2 points, the expected value is just this, right? The expected value of x1, x2. This is the average. So we say that this is expected value of x. This is a proxy for expected value of x. This is not exactly the expected value of x, but if I say that there are only 2 points now, and it is just the x1 plus x2 by 2. So now, if there are multiple points, you'll have to take the average over all of them. But let's start with a simple 2 points. The proof is just extending these 2 points to multiple points, and then we just follow it. We have done it in the past. So if this is the expected value of x, which is in the middle, right? So what you will see is, this is my value. This is my f of expected value of x, right? Just from the graph, clearly, I can clearly see this is f of expected value of x. Similarly, I have f of x1 here and f of x2 here, right? And now if I take the average value, it's like f of x1 plus f of x2 by 2. So it will be somewhere here. You can clearly see that the expected value of fx is, which is the average of these 2 points, is clearly above. So this is strictly greater. So this is how you can remember Jensen's inequality. Okay, so the math aside, what did we learn? That we learned that the KL divergence between 2 distributions is always positive, and the distance between these 2 distributions can be measured in terms of KL divergence, and minimizing the KL divergence between the model and the data is equivalent to maximizing the likelihood of the model. That is MLE. So now what we will do is we will be starting off with what is called latent variable models. In the next half an hour, we'll be seeing what are called mixture models, and they will be serving as the foundations for understanding variational autoencoders, GANs, and whatnot, diffusion models, and so on. So these classes of models are called latent variable models. What latent variable models mean? Latent variables models mean that real data, this comes from this hypothesis that real data, although it would be high, very, very high dimensional, say real images could be 256, 256, 3, and you have so many possibilities of each of these images. But real data, if you can imagine, so say each of this pixel in this 256, 256, 3 can take 256 values themselves. So it takes 256 values. For example, it takes 256 values. So now you tell me how many different images that you can, random images can you make? You can clearly make, so if it takes 256 values, each pixel, you have 256 options. So you have 256 into 256 dot, 256 squared into 3 times. So it is 256 to the power 256 squared into 3. This is the number of images that you have, could make even for a discrete image, leave an analog image. But human faces, for example, would be having a very, very particular spatial structure, something like faces here and so on. So when there is a spatial structure to that, most of this face automatically goes, because you know that if the eyebrow starts here, it will be an eyebrow next. This is redundant information. So human faces actually will lie on very low dimensional space, subspace. These are not exactly subspaces, these are called manifolds. So the manifold hypothesis states that any structured data except noise is going to lie in a very low dimensional space. Therefore, instead of trying to understand the very, very high dimensional space, it's often very beneficial to understand the low dimensional space instead. So how do we learn the low dimensional space? For example, I'll give you an example. Say force is a latent. And when I draw this diagram over here, is what I'm showing. This is called a causal diagram, which means that once I know Z, I can just infer X from any function that we will learn. We'll know how to learn this function. So for example, say you know force, right? Force will give you acceleration, velocity, and position in Newtonian mechanics, right? So if you just want to know to force to acceleration, you will just do force is equal to mass into acceleration, or in other words, acceleration is equal to force by mass. So if you just know the force, you know the acceleration, and eventually you know the velocity and position. So the only one latent variable, force, is actually causing the particle to have different acceleration, velocity, position, and things like that. So this is how you can imagine a latent variable to be. So for example, if you say you have, I'll give you another example. Say that your human faces could be explained by 4 or 5 features. Say 5 features. And I write them as Z1, Z2, Z3, Z5. Say this is the shape of nose. This is male or female. Size of hair. Complexion. And so on. And similarly, eyes and things like that. These sort of things, if you just shift around a little bit, I will be able to create a human face. This is the idea, right? These are like tuning profiles. They're like sliders that you can slide around to get data. So the idea is there is a function. So for example, the function here is 1 by m into f. So the function f of x is 1 by m into x. There is always for the force equation, if you want to know acceleration. So there's always a function that maps between the latents to the data. So this is what we've thus, it is easier to learn this function, which is map a set of low dimensional latents. For example, latent sampled from normal 0, 1, which is easy to sample, latent sample from uniform 0, 1, which is easy to sample, latent sample from Bernoulli 0, 1, or Bernoulli for P, and so on. If you can sample from this and I can model f of x, I can get the data. That's the hypothesis. And how will I do that is the question that we'll be seeing throughout the course. So the idea is the latent is in full control, in our control. What we can do is we can completely control the latent, what distribution we sample it from. But the data, we have to learn a function that maps from the stereotypical latent to data, right? We will learn that function. And once we're able to learn that function, so this is just transformation of random variables. Once we can do that, we have this entire Pandora's box in front of us, because we can sample the latents, we can pass it through the function, and we'll get an output. Right? So let us try to understand this extremely important algorithm called expectation maximization. And when I'm going to show you expectation maximization, I'll be teaching you the first latent variable model, which is the GMM. You could do similar things with any other function, or a mixture model is what you're going to study. It's going to study mixture models. Mixture model as the first latent variable model. Okay, so now say, I'll give you an example first. Say data comes from this distribution. So this red points over here, these are data. Say these are your data points. And I want to be able to sample this data. So you can clearly see that there's this large density here, there's smaller density here, and then there's a very small density here, bump here. So if I have to sample, I may be very inclined to fit a set of Gaussian distributions, which is this bell curves. Wherever you have this high densities, you will have a bump, and where you don't have this high densities, you will have shorter bumps, right? So instead, say if I have k Gaussian distributions. So now you have to say, so here there are 3 bumps that we have. So how do I fit the data? I'll say that Z will tell me which Gaussian data comes from. So this data can be sampled in 2 steps. First, I can sample Z from a multinomial distribution of alpha 1, alpha 2, alpha k. If I consider in the kth class, your data, let us say X is the data. We will say that this is going to be distributed as, this is the notation I'll follow. X is the random variable, is going to have the mean mu k, kth mean, and kth standard deviation or variance, covariance. Right? It will have k covariance of k or sigma k and mu k as the mean. So if you can clearly see that your data p theta of x can be sampled in two steps. First, you sample from this random distribution, which is the, say, what is the probability of z equal to k, that you have sampled the kth latent, or the k, the realization of a latent is just alpha k. So this z can take values between 1, 2, dot, 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 k. There are k categories, k Gaussians, which will help us decide which Gaussian to sample from. So you can clearly say that p theta of x can be written as the integral of p theta of x comma z pz, because I don't know what is the single probability of z. When I don't know, I will add the latents, model joint of data and latents instead. If I don't know, I'll join the model the joint, sorry. So once I do that, I can do this. I can do p theta of x. I just using Bayes rule, conditional probabilities, I can do this. So once I do this, since it is this is not a continuous, this is a discrete distribution. If I'm writing integrals and it's a discrete distribution, be rest assured you can put them as summation of p theta of z equal to k, p theta of z is equal to k, which is nothing but summation of and k equal to 1 to capital K. That is the number of clusters that I have. Say it is equal to k. That is, we have already said that this is alpha k. And this is normal distribution of x, mu k, sigma k. Right. So now k equal to 1 to k. So now if I write down the log likelihood of the data, this is equal to k equal to 1 to k log sum of alpha k, normal xk, mu k, sigma k. So once I write down the log likelihood, I could, now if you ask me what are the parameters of the model, what are the parameters? Parameters are alpha k, mu k, and sigma k, right? So now I could do one thing. I can take the derivatives of log p theta x, alpha k, and so on, and do gradient descent and try to do maximum likelihood estimation, where I maximize the log likelihood. But this entire problem makes it, it's a bit difficult because you have a log sum of expectation. Log sum of expectation. Once you have a log of sum, these xk's and sigma k's, they are intermixed with one another. And it makes solving this equation a very, very computationally intensive process and a difficult, intractable problem at the end of the day. So instead, what we say is we will not try to maximize the log likelihood directly. We'll be trying to use something called as a variational distribution. A variational distribution q of z given x tries to model the conditional distribution of the data in the real model. So this is the variational distribution, and this is the model conditional distribution. Or often you can call it the posterior distribution. Posterior of the latent. Right? So the conditional distribution of the posterior, you want to make it equal because it's very difficult to learn this joint because this joint has this all the sums over all the P of Z's. So we'll see how to do that. So what did we learn? We learned that we can write down if we have multiple distributions, you have a latent that explains which multiple a mixture of exponentials or mixture of Gaussians, a mixture of distributions, a latent that tells you which one to sample from. It gives us a summation over all these normal distributions. And we have a log outside, which we cannot directly optimize for. And therefore, we'll have to solve this mixture of exponentials or mixture of normals here using something called as an expectation maximization. So what we will do is we'll first derive what is called as the elbow or the evidence lower bound, and then use it to do the expectation maximization algorithm. So for the time being, remember that this is my model that I have. This is the joint distribution of the data. This is the log likelihood of the data. Once I have the model parameters, I can compute the likelihood directly, but getting these parameters or optimizing them is a bit difficult. So now we'll do three things. We have shown that if K are K normals, and we have assumed them to be this, and we have got the joint distribution or the marginal distribution of the data. And now what else do you have? So again, if there is this underlying distribution where there are multiple bumps, I want to model it using multiple Gaussian distributions, right? And it could be multidimensional Gaussian distributions. Data could come from any norm distribution. So X could be any in D-dimensional space, right? So now let us derive what is called the elbow. The first step is the elbow. I am telling you that I cannot directly optimize for P theta of X in a mixture model, computationally intensive. Okay, so instead of doing that, what we can do is we can say, let's do this trick. So let us write down P theta of X or log P theta of X as log of the integral of P theta of X. Just the same thing as we did in the previous, when we do not know the data's distribution, when we want to explain it through a latent distribution. So we will add the latent and marginalize it out. This is be equal to log integral of P theta of X comma Z. And I will introduce this because I want to learn this also. I will introduce this distribution now. I will multiply and divide this with the same value, right? What it actually helps us in doing is multiple fold. It helps us with multiple folds. So now, as soon as you guys can see that this is an expectation over this. This is an expectation over Z sampled from Q distribution, the variational distribution of P theta of XZ by Q of Z given X. Now, this is log of the expectation. So now, if I say the log of the expectation, so this is F of expected value of X, right? And that is greater than expected value of F of X. Now you'll be wondering, I just wrote down the opposite because the expected value of Fx is going to be above for a convex function, but now, sorry, it's not wrong because log is a concave function. Concave function. So the expected value of these 2 points, the F of expected value is above the expected value. That's the idea. So the log, if I take inside for a concave function, it's just going to be for concave function. Opposite of convex. Right? So this can be written as expected value of Z. Now this solves this X log sum of expectation. See, now log goes inside the expectation. Now we can solve it easily. So this is called the elbow or the evidence lower bound. Now you may tell me that, okay, but how does it help? It helps because I can fit this. I can optimize this. This I can if I maximize this automatically, if I maximize lower bound on log p theta of x, I am guaranteed to get better fits. Okay, that is what is guaranteed to me. Now I have derived the elbow. Now I will show you that the expectation maximization algorithm will learn an increasing sentence of or increasing sequence of likelihoods. Now you will tell me you have not even defined what is EM algorithm. What are you even saying that you will show that this algorithm works? So I'll tell you that the entire algorithm is in the elbow itself. So if we see the elbow, so I will be writing the elbow. I'll be using a notation now. From now on, the notation that we'll be using is f theta of q, where this is the parameters and this is the model or the variational model. Okay, this I will be saying is the elbow, which is expected value of z in q log of p theta of x comma z by q of z given x, right? So as soon as I get this, I can do some computations. What I can do is I can write this as log of p theta of z given x into p theta of x. Now, if you're already following, you will see what is coming. This is equal to, what do we write? This we can write as expected value of, or the negative of the expected value of z in qz of log of q of z given x p theta. I've just inverted the log of z given x and px plus the expected value of q z sampled from q log p theta of x. You see, this function here is independent of z. So if it is independent of z, you can just take it as a constant and pull it out. So it's the expected value of 1, which is 1 into log px, which is equal to, and this term here is the integral of q of z again, z given x, log of q of z given x. If you recall my definition of the KL divergence, you can clearly see this first term to be theta of x. This first term is just the KL divergence. So I can write this as log of p theta of x minus the KL divergence between q of z given x and p theta of z given x is equal to the f theta of q, isn't it? That's what I wrote. So now I can say that log p theta of x, which is the likelihood function, L theta is equal to f theta of q plus dkl q of z given x p theta of x. So you can clearly see now I have another very, very important equation that links. The equation is, I'll just continue from here. Equation linking What are you linking? Equation linking the likelihood and the variational objective. That is the elbow. The elbow f theta of q can be written as the f theta of q plus dkl of q of z given x and p theta of x can be written as the likelihood of the data, right? This is what you can write this as. This is what we have shown just now. So now recall the quality of the KL divergence. In KL divergence, what I can do is, what can I do? I can set that if q of z given x is equal to p theta of z given x, then dkl is equal to 0. And I have f theta of q is equal to L theta. Right? So this is a very important observation. Otherwise, dkl is greater than 0, and therefore f theta of q has to be less than L theta. So this is what we had shown just now, right? So if this is another way to show the same thing. So we just showed this is L theta, right? This is L theta and this is f theta of q. So we have already shown L theta of q is greater than f theta of q, and that's what we are showing again here. So two things, that these is always less than equal to L theta, and equality if and only if q is equal to p theta of z given x, right? So this can be interpreted in this form. Say, before I go on to the form, so now say we want to learn an algorithm to do it. Let's define a very simple algorithm. I can clearly see I can make them equal if I equate q theta to be equal to p theta. So let us define an algorithm called as the EM algorithm. Where we initialize q theta, q of z given x, and theta, so is our alpha case, could be anything. For currently there are alpha case, mu case, z case, sigma case, for k equal to 1 to k randomly, and then repeat. What will I repeat? So first I will try to make these two equal. So if I have to make these two equal, what will I say? I will say dkl, this is the E step. So it is a 0th iteration. At the 0th iteration, 0th iteration, 0th iteration. So repeat. So dkl qt what are we trying to do? We are trying to say that qt is the arg min of all q's of dkl, q of z given x, and p theta of z given x. Once I do that, I can just drop this term out, right? Because if it is the minimum, I know for most of the models, this is equal to 0. This term goes to 0, which is the minimum. Therefore, qt is nothing but qt z given x is nothing but p theta, where it's the tth iteration of z given x. We can equate them to be equal to each other. So if we equate them to each other, KL divergence goes to 0 and minimizes and sets f theta t qt plus 1 equal to L theta t. So we have obtained the elbow, which when it equals to the likelihood. This is step 1. In step 2, what I'll do is, in step 2, we will now remember this theta t may not be optimal. So now we will fix. This is called the M step, maximize step. This is the expectation step. In the maximization step, what will I do? I will do theta t plus 1 is equal to arg max of theta. And I will do f theta of q t plus 1. Right? I will fix after fixing q t plus 1. So this is something like this. So remember, again, recall. So if I have this graph over here, this is here my parameters theta, and this is my likelihood L theta. I would have things like these. Say I have a step here and I have a step here. This is my theta t. This is my theta t plus 1, which I'll tell why it is going to be better very soon. We can clearly see the likelihood of theta t plus 1 is more than theta t. Right? Here, I'll say that this term over here is the KL divergence between Q of Z given X and P theta T of Z given X. Okay. And this term over here is the, where do I write it? Where is it? Is the F theta term that I have, all right? So this term over here is F theta of Q. So I want to make F theta of Q as large as possible and make it equal to LQT. So this scale divergence is what I want to set to 0. So I will have a line like this or a curve like this along which the scale divergence will be 0. So you see at this maximum point for a particular theta, the variational distribution maximizes to the likelihood function equal to 0. The KL is equal to 0 on this line, right? So now you may ask me, why are you showing that the likelihood functions are improving over time? This is how I'll show you the proof to be. Say, what are we trying to maximize? L theta t is what we have, right? At the parameters at likelihoods under parameters theta t, iteration t. This is, you can know from the property of the elbow, this is equal to F theta of Q for all Q. Yes or no? Or rather F theta t of Q for all Q. This is from the idea that L theta t is equal to F theta QT, or sorry, F theta Q for all Q plus DKL Q of Z given X, P theta T of Q of Z given X. Right? This is why we set this to be equal to this, right? So we can clearly see that this function, F theta Q for all Qs, is going to be lesser because you have a positive term that is added. This is positive. Therefore, clearly the right-hand side is going to be less than the left-hand side. So for all Q, this is going to be true. Next, what can I say? The E step will tell me, what will it tell me? This is going to be the likelihood of, so I will set Q to be, in the E step, I will set Q to be QT plus 1, isn't it? If I set it to be QT plus 1, then I can say, this is from elbow, I'll be able to say that the likelihood at that is equal to F theta of QT plus 1. Because QT plus 1 Z given X is equal to P theta T Z given X. Therefore, DKL is equal to 0. If DKL term goes to 0, then we have these likelihoods to be the same. The E step tells me setting Q to be Qt plus 1, I get the likelihood at the tth instant. So clearly, at this point, this is Qt plus 1. Here it is Qt plus 2, and so on. Setting the likelihood at Qt plus 1 is going to give me this equation, right? So now, this is f theta t. So now I say, in the maximization step that I have over here, I'm going to get another theta that maximizes over these f theta terms. So what I'll do is, so this is for a particular theta t, right? So now if I say that I have arg max over all thetas that is possible for ft, qt plus 1, right? So this is by design that I have the maximum of the function is always going to be sorry, I wrote the equality in the wrong side. The maximum of a function by definition is more than the function value at an instant, at any instant, sorry. So here the instant is t. So now I have obtained this equation. So this also I know is equal to f theta t plus 1 qt plus 1. Right? So now I have got this equation of this is from the m step. So I use the e step to get this equation, m step to get this inequality. So now I know L theta of t is greater than f theta t plus 1. So let us write it down step by step again. F theta t qt plus 1. This is E step. This is greater than f theta t plus 1 qt plus 1. This is the M step. So now as soon as you do this, remember we showed using the elbow that the likelihood is always going to be more than the elbow. So this is less than equal to L theta t plus 1. This is from the elbow. So therefore, we can say that the likelihood at time t is going to be less than equal to the likelihood at time t plus 1. So, and so on. So we learned that if we, under this assumption that the likelihoods or the free energies, if we first take an expectation, equate the Q values to the P theta function. Next, we update the model parameters. Where is it? Yes, here it is. So first, if I take the E step and get the best variational distribution, and then I take the M step and I get better parameters, then I automatically get curves like this, where the likelihoods keep on increasing, right? Okay, so this is my likelihood at time t, and this is my likelihood at time t plus 1, right? And this curve that I have over here, this curve is the elbow function. And the rest of that is defined in terms of the KL divergence. So the f theta of Q, negative of this is often called as the free energy. From the Gibbs free energy in physics, this is often called as the free energy. The elbow is often, the negative of the elbow is called the free energy. Because this is the amount of energy you can get for free at a particular by setting the KL divergence. And the KL divergence is what you'll be setting to 0. This is what you want to maximize to be equal to the likelihood. You want the free energy to be the maximum. That's the idea. Okay, so here we learned about the EM algorithm, and we learned that it is always going to give me likelihoods that increase, likelihoods that are non-decreasing, right? And now we can do it we can update set for a couple of seconds. If we write down the equations, we can do the same update for GMMs as well. So let us do it for GMMs. The next 10 minutes we'll be able to do it for the GMMs. Update for GMMs. EM update for GMM. right, for Gaussian mixture models. Okay. So what is the update for the Gaussian mixture model is what we'll see. First is the E step. In the E step, what do? We say that Qt plus 1 Z given X is equal to P theta of Z given X. So now recall from the very beginning, what does GMM assume? The GMMs assume that P of X given Z equal to K is distributed as normal mu K sigma K, which is equal to, if you know your multivariate calculus, 2 pi to the power d by 2, the determinant of the root of the determinant of the covariance matrix, right, into e to the power minus half x minus mu K transpose sigma K inverse x minus mu K, right? This is how we define our what do you say? We define the PDF of a multivariate Gaussian. So let us quickly do the math here. So Qt plus 1. So again, these are discrete variables. I know that P of Z equal to K is alpha K. And once I've given the latent Z, I can model or the output the distribution in form of a normal distribution, a particular mean and variance. So let us do it. So Qt plus 1 is at time instant t. So this I do not know. So this is proportional to saying, but I know using Bayes rule, this is equal to Z equal to K. Write this as Z equal to K given X into P theta T of Z equal to K. So this is equal to, or this is proportional to, this we already know is alpha K at time T. And this is the normal distribution we have already defined from 1 and 2 here, or A and B. From AB sigma K. So now you must remember that the probabilities must sum to 1. If the probabilities must sum to 1, this summation from K equal to 1 to capital K should be equal to 1. And therefore, you can just normalize this as follows. So this is just very simple. You just get a weighted norm of the Gaussians. So how do you interpret this term? You interpret this as you take a data point, you fit it to the Gaussian, you see what is the PDF value you get, multiply with the probability of getting that Gaussian and divide by the total it belonging to every Gaussian. So you have multiple Gaussians like this, you get a new data point, you compute the value for each Gaussian, it will be small for this, and multiply, and for the probability of being in a particular Gaussian, this tells you probability of being in a Gaussian, being in Gaussian K. Okay, so this gives me and I will define this as, so they say this is defined for the data point I. So this is, you have n data points. If you have n data points, I define this for the data point I will write this as QKI, T plus 1. This joint distribution, I'll put as this as the notation. Right now is the M step. What is the M step? You want to maximize T plus 1, mu T plus 1, and alpha T plus 1 as the argmax over alpha, mu, and sigma for what? F theta of Q. t plus 1, right? Now, what is the definition for the elbow? If you recall, this is equal to, we had written this down as again log of p theta of x comma z by q of z given x, the expected value over q, isn't it? Very good. And we are trying to maximize argmax. So let's do it. What is the, so this we can write the expected value as k equal to 1 to k q t plus 1, or this is the expectation value over qt plus 1. We fix qt plus 1. Right? Qt plus 1z is equal to k given xi. Right? And this is over all the data points. This is over all data points, I equal to 1 to n, all data. So this becomes log of p theta of x given z equal to k, right? Into p of z equal to k. Very good. And you have minus I equal to 1 to n summation of k equal to 1 to k q z is equal to k given xi log q of z equal to k given xi. So this is, you can see, is independent of theta, independent of alpha, sigma, mu. So if it is independent of all these terms, so I can just drop them. This is what we have seen. This is, we have to define for every alpha k. So I'll k from all the clusters, all the Gaussians. Okay, so I can write this down as, so this is equal to alpha k. So this is alpha k. Oh, sorry, not alpha k. This is q ki q ki, and you have a sum over I equal to 1 to n, I equal to 1 to n log of 2 pi d by 2 sigma k to the power half exponential of e minus x minus mu k sigma k inverse x minus mu k. So this is what we have. Subject to what we have a constraint as well. Summation of alpha i's or alpha k's, k from 1 to k should be equal to 1, because this is a probability distribution. Right? This is just saying probability of p of z equal to k is equal to 1, k equal to 1 to k, isn't it? This is all we are saying. Right? So so if we have to optimize for that, so this is my mu k sigma k alpha k. I will have to write down the Lagrangian as we have seen. So if we have to, because there is this constraint, so you will write this down as summation of I equal to 1 to n, summation of k equal to 1 to k, qki p plus 1. I will drop constants, dropping constants. So I'll dropping constants. So if you drop constants, you can write this as plus c, and we will write this as half times log of sigma k with a negative sign. This is a determinant of this, minus half times x minus mu k sigma k inverse x minus mu k. Okay, so this is the first sum. And to add the constraint, I will use the Lagrange multiplier. And I'll say 1 minus summation of I equal to 1 to k alpha I. This is how you do that, right? So now if I first parameter I'll find is I will do DL D alpha K. So if I just do DL D alpha K, I also have a term here. Just a moment. I have this term as well. So I will be able to write down plus log of P theta of Z equal to K as well. I forgot that term. Yeah. So I will be taking the derivative with respect to alpha K. This is nothing but alpha K. So if I take derivative with respect to alpha K, I will get I equal to 1 to N QKI, because only this term will be existing only for the K derivative by alpha K, right? Plus lambda into 1 minus 1, because the derivative of all other terms of all alpha k's will go to 0 except the kth alpha. I'll just put J for your convenience. If I put J, this will become J, and this will become only the jth term becomes 1, rest are all 0. So your lambda is equal to summation of QKI. QK is it? This is the jth term. So the jth term only remains QJI T plus 1 by alpha J. And I'll set it to 0 because that's where it's optimized. And this is equal to 0. That is equal to lambda. So sorry. So I've already written it down. So lambda alpha J is equal to summation of I equal to 1 to N QJI T plus 1. So now if I sum over all the J's from 1 to K, J equal to 1 to K, this term should go to 1. So only lambda remains. Lambda is equal to summation of I equal to 1 to N, J equal to 1 to K, QJI T plus 1. Now again, there's this intelligent trick over here. This term is again a distribution. Remember, this is Q of Z, the J xi. If you sum over all J's, this is equal to 1. So this goes to once for all the n points. So this is equal to n. So lambda is equal to n. So now I get 1 point. I get this equation to be alpha j is equal to summation of I equal to 1 to n QJI T plus 1 by n. So you're actually checking sort of how many points are in the jth Gaussian. So it's a soft clustering is what you can clearly see. So now once I get alpha t plus 1, now next similarly I can do dl d mu k. If I can do dl d mu k, you can clearly see with a little bit of, you can look into the Wikipedia matrix algebra page. We have done those algebra before in class as well. When you have a matrix multiplication like this is of the form x transpose sigma x. The derivative with respect to x turns out to be sigma times 2 times sigma x. You can think of it as a quadratic because this is actually a ax square. So this should become 2ax in a one variable calculus. So for mu k, if you do a similar derivative, if I take a derivative, I'll just copy this entire term. Just give me a moment. I'm just copying this. Yeah. So if I copy this, I'll erase this out. Right? just to see these terms clearly. So if I take the derivative with respect to dl d mu k, you can clearly see only this term alongside this terms remain. So you can write this as k equal to 1 to k. Only the k, or rather again, j would be a useful term to use because k's have been used in the summation already. So q j I t plus 1 summation of equal to I to n, and you will have, where is it? You'll have only this term being taking a derivative of using this property 2ax. So you'll get negative of sigma k inverse xi minus mu k. See here, this mu k, just you can take a transpose operation and just, or inverse operation, mu k you can multiply. This goes to 1 on both sides. So you get, and also multiply minus mu k. So this term becomes I equal to 1 to n q j I t plus 1 xi minus mu k equal to 0. So you'll get mu k summation of I equal to 1 to n q j I t plus 1 is equal to summation of I equal to 1 to n q j I t plus 1 xi. And what is this value? We've already found this for I equal to 1 to n. Look at this from the Lagrangian multipliers. We have already got that. So if I take the summation, so this is the summation over all I equal to 1 to n. So mu k, I know all these values already, but there's a closed form is what I'm trying to say. I equal to 1 to n q j I t plus 1. I equal to 1 to n q j I t plus 1 xi. Sorry, not the k, it's the j term because I took derivative with respect to j. So you see this is a weighted average. Weighted average of each data point. Right? So now this term here we have seen to be equal to what? Lambda is equal to n. So I can write this as, so we have seen n times alpha j to be equal to summation of j equal to 1 to k, I equal to 1 to n, q j I t plus 1. So which term is what we need? We need, just one moment. We need the summation over all the data points, right? So this is what we desire to have. So instead of taking a summation, we can directly get this from this equation. Sorry. So here, if I write this equation, I will get alpha j is equal to alpha j into lambda is equal to summation of I equal to 1 to n q j I t plus 1. So which this is equal to, we know lambda is equal to n, so n alpha j. Right? So this is equal to n times alpha j t plus 1. Finally, we will do dl d sigma k and we'll get, so you can, so if I write down the same equation over here, I'll just paste it. So again, so you can see, you can again look at that matrix derivative cookbook. There you'll be seeing this formula, dl, derivative of a determinant is given by the determinant into the inverse. It's very easy to derive, but we're not doing it in the interest of time. So dl d sigma here, sigma j, is clearly I equal to 1 to n minus can be removed because we have my minus throughout, qj I t plus 1 sigma j inverse. And since we have a log, I also have a sigma j 1 by sigma j when you take a derivative, minus the derivative of the trace of xi minus mu k xj minus xi minus mu j xi minus mu j sigma j inverse. Why did I write this as the trace? You can clearly see that this term is what I wrote as the trace. So you know that this property of trace of AB is equal to trace of BA. It's a cyclic property. Similarly, trace of ABC is equal to trace of CBA or CAB. Sorry, you can take it in a cyclic order. This is the reason I could write it. So once I have the trace is a linear operation. I can take this derivative inside, and I can get I equal to 1 to n qji t plus 1 sigma j inverse minus xi minus mu j xi minus mu j sigma j to the power minus 2. This is another property of the trace, and I'll set it to 0. Once I set it to 0, you can multiply sigma j squared on both sides. And as soon as you do this, you get sigma j summation of I equal to 1 to n qji t plus 1 is equal to, so x minus mu xi minus mu j xi minus mu j transpose summation over I equal to 1 to n of qji t plus 1. So you can just do the algebra and you'll get sigma j is equal to 1 by n alpha. Similarly, same way, because this summation is equal to 1 by n alpha, summation of I equal to 1 to n qji t plus 1 xi minus mu j xi minus mu j transpose. So this, if you know, is the weighted covariance matrix. So you can see we have got all the terms now. We have got all the terms, the update for all the terms, and it can be shown that these terms converge. So this is, you are computing covariances, you're computing means, and you're taking what is the weight of each of these data point in a particular cluster, and you're doing this and you're updating each of this step. We'll see that this is very similar to the EM algorithm for the k-means clustering next session. And till then, you can revise these derivations. So you can see, first of all, we saw that the EM algorithm can be used for latent variable models where the latent is not separable for the likelihood. And we showed that the EM algorithm is going to converge. It's going to give you better likelihoods each of the times. And finally, we showed the update steps for the EM algorithm. We showed both the E and the M step for the exponential, for the GMM. Your homework is, you've been following till now, your homework is in the Teams channel, post the mixture of exponentials distributions for x in real number. So you have only one feature. You can try and put the exponential. So x is distributed as exponential lambda I. So it's like alpha I summation of exponential lambda I. This is your px. You try to do the update for this mixture of exponentials as well. So we have been seeing that with the use of the exponential with the expert variational distribution, I've been able to find the closed form solution for the E and M step. And if I do it iteratively, I'll get the exact Gaussians or the normal distributions that I showed here. The data will actually fit this data in this form. And you may ask me how many number of data points, how many number of Gaussians to fit. That's an hyperparameter. You can check which fits your data the best, right? And with that, we'll stop today's session. We'll do similar coding. This code is already available for the previous sessions. I may share it again with you all. And other than that, you can practice and ask doubts in the group if you have any. I'll be happy to take them. So thank you. I'll stop recording. See you in the next session where we'll be starting with variational autoencoders.